In the previous video, we solved this system of linear equations using only those 3 allowed elementary operations. And at the end, we got to a state that said that x minus 2z equals 5, or x minus z is equal to 5, no 2 there, and y plus 2z is equal to 0. And 0 is equal to 0. Those were our 3 elements in our system, in our reduced system of equations, or simplified SLE. And we identified that we could not take this any further. It was not possible to further simplify this. So I looked at it and said, it appears that I can pick anything I want for z. I'm completely free to choose any z value I want and then get x in terms of z and get y in terms of z. That freedom to choose anything I want for z is going to mean that this has an infinite number of solutions. I can't write them randomly. There's some order to this. It isn't like infinite, choose anything you want, infinite. It's infinite, but by the way, you have to follow some rules, infinite. The rules are, if I choose something, some number for z, that's going to constrain or define what x and y are in terms of that number. So if I let z equal t, then x is equal to 5 plus t. Y is equal to negative 2t. That's what we're forced to conclude. And then our solution, I know I put this in the last video, but I want to highlight something I didn't have enough space to get into, is that x comma y comma z is equal to 5 plus t, comma, negative 2t, comma, t. Now if I asked you, what is this? What did we just write down? What type of object is that? It's not really a fair question until I show you what you can do with an expression like this. I'm going to write this as 5, 0, 0 plus t, negative 2t, t. And then I'm going to do one more step. 5, 0, 0 plus t times 1, negative 2, 1. Now what is this? You have to know this. What geometric object is written at the very bottom in blue? It's a straight line. This is x of t is equal to a point P plus t times v. Equation of a line. This was one parameter family of solutions. Point parallel form. Now I don't expect you to do this. I don't expect you to take a solution vector 5 plus t negative 2t, t and write it as a line in point parallel form. But it's valuable, I think, to be able to connect this back to what we were talking about before. These are still the same geometric objects we were describing. We had x minus z is equal to 5, y plus 2z is equal to 0. Our original expressions actually were 3 different planes. What did we just find? We were given 3 planes. We're asked to solve them. We came out with a line. What we found is we found the line of intersection of 3 planes. So you have these 3 sheets of paper extending infinitely in all directions, and they're angled in different ways, and we found that they cross on a line, and this is the line that they cross at. That's amazing. That's geometrically incredible. Let's do another one. This one has x's and y's in it. There's no z, so this is just 2D, not 3D. These are 2 different lines. Let's solve the system of equations. Now we're going to have to do something we didn't have to do in the last example. We're going to have to put them in standard form first. So first, put SLE into standard form. So the first equation I'm going to rewrite as 2x plus 2y equals 2. I added 2 to both sides, or 2y to both sides rather. And the second equation, I'm going to add 3x to both sides. So 3x plus 3y equals 6. Let's keep going now with the actual solving. What I'm going to do is, instead of replacing equation 2 with, let's say, itself minus 3 over 2 times the other equation. So instead of doing that, what I'm going to do is I'm going to multiply each of these two equations by a scalar, by a constant, because that's one of our 3 allowed operations. I'm doing that because there's a 2, 2, 2 for the first one and a 3, 3, 6. There's a common factor in all of them. And I can multiply the first one by a half and multiply the second one by 1/3 and simplify each of them. So make the number smaller. So that's my first move, is replace equation 1 with equation 1 multiplied by a half. And at the same time, I'll do 2 moves in one. This is sometimes dangerous, but I'm doing 2 different moves to the lines separately. I'm not mixing operations together, like multiply this by a constant and then subtract that line from another line. Don't do that unless you're like super confident you can keep track of everything. It's easy to lose track of these things. I'll replace E2 with E2 multiplied by a third. And it's okay to call it division by 3 if you want, but I'm going to follow the template that we're just multiplying. Okay, so when we multiply equation 1 by a half, we have 2x times a half, which is just x, 2y times a half, which is just y, and 2 times a half, which is just 1. When I multiply the second equation by a third, I get 3x times 1/3, which is just x, and the next part I just get y, and the last part I get a 2. All right, next move. I'm going to replace equation 2 with equation 2 minus equation 1. So inside this move, equation 1 is going to stay the same. X plus y is equal to 1. Equation 2 becomes x minus x, which is 0, y minus y, which is 0, and 2 minus 1, which is not 0, it's 1. And we're done. If this was a practical application, this may be a disaster. Like, this is time to go and deal with bad people. But if this is a math test, an artificial scenario like a math course, this is the greatest thing in the world that can ever happen to you. Because it means that you're finished. You're done. You can say that there's no answer. That second equation says 0 is equal to 1, and you know that that's not true. 0 is definitely not 1. You got one person with 1 pizza and someone with 0 pizzas. That's not the same. In no universe at any point in time, in the past, the present, or the future, this will never be true. So 0 equals 1 is nonsense. No solution. There is no key that will simultaneously unlock both of those doors at the same time. No solution to the SLE. We can stop as soon as we see anything, I was going to say something, but anything like 2 equals 3, or 7 is equal to 1, or 3 is equal to 0, etc. Anytime we come to a statement that reads one of those ways, it means that the SLE has no solution. So artificially, if we don't actually care about the outcome of the problem, if we're not doing this because we're doing a supply chain management problem or looking for an answer that we desperately need, if all that we're doing is just solving a question on a math test, This is the best. Like, this is time to celebrate because you're finished. There's no more work to do. Now, all these different scenarios that we just went through for solving systems of equations, I'll go through them quickly, going back through the examples. We saw one that we got a concrete solution for. X was 2 and Y was 1. We did a sequence of moves, got our solution. We did another one that was more complicated. We did a sequence of moves and we found that there wasn't a unique solution. There was a family of solutions that were related to each other through a parameter. And this one's kind of mysterious still. How did I know I could let z equal t? Why didn't I let y equal t instead? Why z? Well, I'll tell you not now, I'll tell you very, very soon. So that was the other case. And then we saw the last case, a system of linear equations that led to no solution. And it turns out that's all there is. Rather than go through more examples using the approach I just showed you, I want to jump to what you will actually be doing to solve systems of equations. You won't be doing exactly what I wrote down in those examples. You'll be doing something that looks a lot like it, but it'll have less writing. You expect this and get this. So when you see the word matrix, I don't know if you even expect this anymore. Maybe 10 years ago, you would have expected the Matrix movie, but I don't know if any of you have even seen this movie or the set of movies. I think there's 3 of them. I don't know if there's 3 or 4. I have no idea. I know I saw the first one. I don't think I saw the other ones. The process that we went through to solve these systems of equations using 3 elementary operations, so swapping the positions of rows, or swapping the order of equations, or replacing one equation by itself plus or minus a multiple of another equation, or multiplying an equation by a scalar. We're going to reframe these operations, and we're going to reframe the components of a system of equations as well. We're just going to use a different language and different notation and essentially do the same thing. It's faster though. We'll begin calling these things row operations instead of elementary operations, but they're the same thing. Instead of calling the equations equation 1 and equation 2, equation 3, I'll call them row 1, row 2, and row 3. So pieces going left and right, that's one row. Then underneath that is a second row. Underneath that is a third row. Going left to right, we'll have columns. So column 1, column 2, column 3, and so on. Each column corresponding to a particular variable. You'll see what I mean when I start writing them down. Introducing this extra language, this extra vocabulary, and this extra structure is helpful for one reason, because it requires less writing. More importantly, once we do this, we're actually defining a new mathematical object. We're defining this mathematical object called a matrix. In this section, or in these sections, 2.2 and 2.3, the matrix is only treated as a shorthand for a system of linear equations, but it's actually a lot more than that. So here's the anatomy of a matrix. The pieces going left and right, as already stated, are called rows. So the first element there we would call row 1. And I'll just highlight that. I'll just highlight row 2 actually. Row 2. And I'll highlight one of the columns, column 3. And we'll talk about positions within matrices using this vocabulary. We'll say, okay, take a look at row 2. Take a look at row 4. Take a look at column 7. So that's how we'll index where we are. Or if we want a particular coordinate, I don't know if you know latitude and longitude for maps. So how far do you go left and right? How far do you go up and down? Well, you certainly know your x and your y coordinates. We're going to use rows and columns to identify one particular position within a matrix, or one particular number within a matrix. So go to column 4, row 7. So how many do you go left and right? How many do you go up and down? And that'll tell you what number we're talking about. So we'll be indexing locations in a matrix using rows and columns. Also, it's important to mention that the word matrix, the plural of matrix is not matrices, it's matrices. And I do not know why, nor do I care. It's just what everyone has agreed to say. I'm sure there's a great reason. Someone can tell me. And I probably already know, someone already told me, but I forgot because I don't care that much. Just a word. So some examples of matrices along with their sizes. The matrix shown first, we can count the rows. There's a stack of, this stack has, you can think of it as 3 plates stacked on top of each other. It's a stack of 3 equations. There's two elements in each of those rows. So we would say this is a 3 by 2 matrix. What's shown here is a 3 by 3 matrix, 3 equations and 3 columns, or 3 rows and 3 columns. A matrix doesn't have to look thick like that. A matrix can be thin like this one. It has 4 rows and 1 column. And it can also be wide. It can be 1 row and 4 columns. A matrix like the last one may resemble a vector. And in some scenarios, we will do operations with matrices we'll do operations with vectors using matrix operations. Just have to be a little bit careful with what we're doing. What we'll do to start off using matrices is we'll take a system of linear equations like what's shown on the left-hand side, 5x plus 2y plus, I don't know why they're not all colored in. I'll color them in now. So 5x plus 2y plus 3z is equal to 7. 2x minus 3y minus 4z is equal to 0. And then x plus 10y plus 8z is equal to 2. Oh. What we'll do is we'll strip out the x, the y, and the z and rewrite that system of equations in matrix form, where it is implied by the order in which the numbers appear that everything in the first column corresponds to the coefficient in front of x. First column is x. Second column is y. Third column is z. The equal sign has been replaced by a vertical bar. And then the constants on the right-hand side are all by themselves. Our original system of linear equations had 3 equations with 3 unknowns. Our matrix has 3 rows and 3 columns. Every equation has its own row. Every variable or every unknown has its own column. We'll always have that. The right-hand side will always be separated from the other pieces with a vertical bar that denotes the equal sign. And we'll always have the same number of elements in each row. If there's a missing element on the left-hand side, then that means that the coefficient in front of, let's say in front of y and in front of z is 0. We have to make sure that all those pieces are there. That's one of the reasons why we were so cautious in the previous material about writing our systems of equations in standard form. Because when we convert them into matrices, not having them in standard form is a recipe for disaster. It will make it likely that it will mess things up. The left-hand side of the matrix is called the coefficient matrix. The stuff in red is called the augmented part of the matrix. So we have the coefficient part and the augmented part. And those are words that we'll use to describe those components. You're going to see at different points in the course the ij being used. These are not the I and j unit vectors. I want to highlight that. Not the I and j unit vectors. This time, I and j just refer to numbers. So the 2, 3 entry is I equals 2, j is equal to 3. It's a very common shorthand in mathematics, computer science, engineering, and it's unfortunate that it has overlap with the unit vectors I, j, and k, but that's just the way it is. You'll have to know from the context what is it talking about. If it's asked for the I, j entry, then it's not unit vectors. Okay, we'll do one quick, actually, we'll continue in the next video. This video is already too long.